Welcome back. So in this lecture we will digress a bit from controls and talk about optimization. Obviously we are going towards optimal control, that's the goal. So in my opinion, no engineer or for that matter mathematician can avoid studying optimization. Many of the results that we are going to see are probably familiar to you, especially the basic optimization results. But then we will move on to functional optimization, and then eventually that will lead us to optimal control in the next lecture. And then there are many different aspects of optimal control. We will touch upon some of the key highlights. And of course, we will go slowly, start with the simplest possible problem in optimization, understand where these results are coming from. And the reason is not that you do not know, but actually the same idea keeps repeating itself everywhere, right? So let's go ahead and see. We'll look at the most basic thing called scalar optimization. Then we will look at the vector extension to it, and eventually we'll go to functional optimization, right? So what is an optimization problem? In English, basically, among a set of candidates, find the best one, right? So there could be many questions there, but we will slowly try to address each one of them, right? So so we define something called a feasible set or feasible space. Feasible set is a more appropriate name for it, which is nothing but set of all possible candidates, right? Set of feasible candidates, set of allowable candidates. So we don't want to find best in candidates that we don't have otherwise some basic qualifications and things like that. So this feasible set is basically all the qualified candidates and out of which we will pick the best one, right? What do we mean by best one? Some quantity should be there defining some measure, some characteristic should be there. Now let's say we're going to say color is one of my characteristics. Unfortunately, between yellow and blue, let's say, you may have a preference. We'll come to the preference in a second, but between yellow and blue, there is no way of saying which one is better. There is nothing like an inequality satisfying these two in terms of less than or equal to kind of an inequality. However, your preference, what we can call it as utility value of each of these colors, we may associate. So we may actually fancily define a function of utility value of each color, right? But then that function will take each color and give a real number to it, and then basically if yellow has 0.3 and then blue has 0.4, then perhaps blue is better, right? In this particular case, let's say higher the better, if you assume. So eventually we need a function that matches the set of candidates, that could be colors, objects, anything, to real numbers, because only real numbers we can compare, not even complex numbers, right? I mean, that's something that we at some point called something called as a full order set, right? Matrices are not, they are not scalar numbers, whereas scalars, real numbers, basically, so a set of real numbers is a fully ordered set, and then we need to have that kind of if you have two real numbers, we can say one is either they are equal or one of them is bigger and or the other one is bigger. So so the objective function essentially is like the utility function that I was talking about. It measures the goodness of the candidate in F, and people call it also a cost function or a utility function. Sometimes we may minimize the cost function, sometimes we may maximize the utility function, right? Depending on the terminology, but in reality, mathematically, none of those things make a difference, and we call that as an objective function in a general perspective. So in the language of mathematics, then this problem can be stated as minimum, over all x in the set F, minimize this function f of x, where f is of course the objective function, or sometimes we may wish to do maximization, right? So F can be anything. F can be set of numbers, set of objects. They can be set of discrete objects, a set of continuous. Color, for example, could be a very continuum of colors and things like that. So it could be a continuum of some abstract objects. It could be discrete objects, right? There's nothing sacred about the structure for this set F. But F, like the small f, the function, is necessarily a real valued function. Otherwise, there's no way of comparing, as I already indicated. So if f is discrete problem, then it's called a discrete optimization problem. And essentially, if you have, let's say, 10 objects in the set F, and then each of those objects in the set capital F, the function will give you 10 different values, right? Or different or equal or whatever. And it's essentially trying to, let's say it's a minimization problem. We have to take a look at these 10 numbers and then find the smallest one. And there is no other approach to discrete optimization problem. If you have 10 numbers, compare every pair of them and then start finding the better among the two, and then compare with the third one, see which one is the better of the two again, and then keep going. And then there could be slightly better approaches by dividing the sets into two and things like that. You can improvise in terms of time, but essentially it's always boils down to comparing two members and then pick which one is better and then move on, right? So in that sense, it's an exhaustive search. We have to search pretty much for every one of the candidates and then see which one is better among all those candidates. So obviously for large problems, suppose if you have I don't know, 1 million candidates and things like that, you have to do this comparison over that 1 million, literally basically the combinations in that many combinations in pairs has to be compared. Now, and there are some very important problems there. I mean, the famous one is the so-called traveling salesman problem, which essentially says we have a bunch of cities. Can you find a path that is covering all the cities without repeating any of the cities? I mean, you should not visit the same city twice. Okay, so that's the pathfinding problem. And then among all such paths, can we find the shortest path? So that's called a traveling salesman problem or a minimum path problem. And something like 10 cities, you will have already 10 factorial or 10 or 9 factorial, depending on whether it's a circular path or not. And a small number like 10, you'll have 10 factorial, which is already in the range of 300,000, or I don't remember exact value of 10 factorial, but somewhere it's a huge number, right? Now, if it is 100 cities, then it increases by much more. And then, as you can see, basically this falls into the category of some kind of exponential increase in terms of the number of combinations that we have to check. And all such problems are considered one of the most difficult problems, and there are some very nice open problems associated with such problems. And there are algorithms, heuristic algorithms that solve these problems, but not really much more than that, right? So discrete optimization problem is quite difficult, and there's not much that we can bank on other than this exhaustive search. And there are, like I said, wonderful heuristic algorithms. Genetic algorithm is one of my favorites. There are other algorithms that people use: simulated annealing, particle swarm optimization. There are so many different methods of optimization. So interestingly, today many times some of the non-discrete and the continuous optimization is actually converted into discrete optimization because we have this computational power. But mathematically speaking, all those problems are quite difficult, and then basically, the solutions that we get are suboptimal. So they're not quite there in terms of theoretically showing something is optimal, but we get some answer that is better than where we started, and then we live with that kind of answer. And therefore, discrete optimization techniques that are heuristic in nature, like genetic algorithms and things like that, are quite useful because we can get a good answer by searching over that space discretely using powerful computers. And that's a technique that we should keep in our mind, right? And if we get a chance, we will talk about them a little bit somewhere in our discussion. But here we will focus on continuous optimization more than discrete, right? So anyway, one small remark, we will focus on minimization problem only, simply because minimization of f of x is same thing as minus of maximization of minus of fx, and I leave that as a problem for you. You know, how do we show rigorously that the minimum of f of x is same as minus max of minus f of x? I mean, it's a good idea to practice on something so simple in terms of how to write a good proof. Right. So that will lead us to basically continuous optimization. So we will look at something called unconstrained optimization over continuous space. And for that, we will start with the feasible set F, being an open set. Okay. So if you have an open set, then the problem is unconstrained, at least in the continuous scenario. And if you recall, an open set is nothing but where every point in that set has a ball around it, which is completely within that set, right? So to define a ball, the space needs to have certain topology, and if you haven't done an advanced course in topology, you may not appreciate that particular part. But the simplest thing is basically, the ball is at a particular center, some distance away and things like that. So the least we need is actually some distance or a norm or something like that defined at that particular space. And this space can be as complex as it can be, as long as this notion of distance or a norm or a topology in more generic terms is defined. And as a side remark, I would want the readers, the audience, to basically perhaps go look up a wonderful book. I believe the title goes something like Topological Spaces from Distance to Neighborhood. It's a wonderful book on analysis. If you're mathematical analysis oriented person, you will enjoy this book thoroughly, because it starts with the notions of basic distance and things like that, and eventually make into a very abstract notion of topological spaces where neighborhoods and things like that are defined quite abstractly. Anyway, so let's get back to what we were talking about. So these open balls, for example, in the standard real number sets, then they are simply open intervals, right? So intervals from A to B without including either of them. But if something like a complex plane or a 2D plane and things like that, then we use norm to define open balls and things like that. And again, the boundary of those balls are not included, and that's why they're called open. And you can actually have infinite dimensional spaces, and then we will slowly solve some of these problems. Perhaps I should. So if you had a 2D space or something like that, then we know, around some center, basically we can define a ball. Let's say something like this. This is a ball of radius 1, where is defined as square root of x1 square plus x2 square and so on. Okay, it is the 2D, so square root of x1 square plus x2 square, right? Now, if it is, on the other hand, is a function space, right? F is a subset of some vector space which is defined to be all functions going from, I don't know, f r to r, right? Now, f itself may be a real valued, but in reality, it takes a independent variable t and produces many more values, and then they most probably will produce infinite number of them, or countably infinite number of them. So therefore, it is that's why they are called infinite dimensional problems, right? And as you can imagine, basically the summation in that particular case will become kind of an integral. So typical maybe perhaps between 0 and t or something like that, typical norm, and then this is what we call as 2 norm, right? And this is it's named after Euclidean norm. And we can also think about other norms, which is simply, I'm going to say, supremum of f of t. And supremum is simply, if you do not find the maximum within it, basically find the nearest number to that. So anyway, you can define many such things, and then basically in all these cases, basically we will look at all functions such that the norm of that, whatever the appropriate norm as the ball. So this is ball of radius 1. Okay. So what we are talking about, if we are talking about open sets, we typically talk about strictly less than 1, right? So hopefully you get some picture. Basically, why do we require openness? We will understand in a second. If f is discrete, then it cannot be open set. You know, by definition of anything to do with open and closed, you will realize that if it is bunch of discrete points, then they're all. It's in fact it's exactly the opposite. They're closed sets, and then unconstrained optimization does not even make sense in terms of definition. But on the other hand, if f is an open set and we can find a solution to the minimization or a maximization problem, then the optimal solution is going to be in the interior. That's obvious. I mean, you know, if there is a solution within that set, if it is an open set, every point is in the interior, if you know what the definition of interior, right? So anyway, that's the nice thing about this unconstrained optimization over open sets. Basically, they give these nice properties that everything can be looked within the set rather than outside, right? So anyway, before we go further in this, let's talk about convex optimization a little bit. Let me write a few things and then basically go back, go away from monotonous stuff. Let's say you know, I have a set like this versus this, right? And I'm going to say this is a convex set, but this is not. Right? What is the definition of convex set? Well, if you take 2 points, the line connecting between these two has to be within that set, and this is not convex because if you take a line between 2 points, and this is not in that, right? Of course, I mean, you can still find some points where it is between there, but you should ensure that every line, every pair of points, the line joining between them should be in that, right? So mathematically, how do we say? Basically, C is a convex set. C is convex if you take a pair of points, then alpha x plus 1 minus alpha y all belong to C for all values of numbers between 0 and 1, inclusive, because 0 gives you, y, and then 1 gives you x and things like that. But typically it's written as alpha between 0 and 1 without including them, right? So this is essentially the line joining x and y. Now then we can define a function on this convex set. Okay, and then again, you know, it's essentially a real valued function, and it satisfies something quite interesting. So f of alpha x plus 1 minus alpha y has to be less than or equal to alpha times f of x plus 1 minus alpha times f of y. Again, alpha is between 0 and 1. So what is this? Well, let's actually look at a function on the real line, and then if you take any interval, open, closed, half open, all of them are convex sets, because you know the line between any of the 2 points will be within that set, right? So I'm going to consider the open set, I mean, so some set like this, and then let's consider a function like this. And perhaps a function like this, right? And if you actually pay attention to this, this is the line joining, let's say, you know, this is x, this is y, okay? And this on the right hand side, basically alpha of f of x plus 1 minus alpha times f of y is the line joining. This is f of x and this is f of y, right? And the line joining these two is going to be above the function value of anything in between. So this is what we see, that is below this line, right? That's a convex function. But on the other hand, if you actually look at two points on, let's say this and this, if you take that x and y, then you can clearly see that the line joining is actually below, and then therefore this is not convex. Okay, so convex is like this is concave, and of course anything like that is at least over this range is not convex, or neither concave nor convex, right? Now just a side remark, basically if you have a straight line that is both convex and concave, and though this may not look like a convex function, we can actually say this is convex on this subset, right? So it's not like convex is defined over the entire real line or space, whatever we are working on. It can be defined for a particular set, right? So let's formalize this entire thing. So for f to be convex, it need not be open and closed, as I indicated already, but only thing, it has to be connected. If it's not connected, we can never get what we want. The entire line cannot be within that. And we already defined this. F is a convex function. Now this is what is quite interesting, and I'll go back and prove. If f is a convex set and f is a convex function on that convex set, and suppose we find this x bar minimizing f, okay, over this convex set script f, then it is going to be a global minimum. So if you have a local minimum, then it is going to be a global minimum, right? So let's say f is there, right? And I know x bar minimizes f, okay? Let's say locally. Okay, what I mean is basically there is a small subset, call it B sub f, such that minimum x belonging to this B f of x is fx bar, right? So x bar solves that particular problem, not over the entire set f, but it satisfies in some small region, right? Then how do I know that this is going to be minimum for the entire set? Well, let's assume that there is some f of y, there exists y belonging to f, okay, such that f of y is strictly less than f of x bar, okay. So then basically this implies f of alpha y plus 1 minus alpha x bar is less than or equal to f of alpha f of y plus 1 minus alpha f of x. Okay, so as you can see, basically this is the line joining x bar and y, right? And if you actually pay attention, what happens is, let's see, alpha is equal to 0 produces x bar. So as you keep increasing alpha, okay, out of these two, basically f of x is big, right? So therefore this is definitely, in fact, anything between 0 and 1, this is strictly less than f of x bar, okay. So and then basically this is essentially saying the entire line joining x bar and y is going to be such that f of x bar is greater than that. But that's a contradiction, because we know that in a region around x bar f of x is kind of the minimum, and then basically you cannot find numbers that are smaller than that, right? Everything has to be bigger or equal to f of x. So that's a contradiction. Okay, so so If you have local minimum, then that's going to be a global minimum, right? And there is another extension of this result, fairly straightforward. We know from analysis, if f is continuous, then it has always on a closed set, then we have actually a guaranteed minimum and things like that. By combining both these things, this nice result comes. If f is a convex closed set or closed convex set, and f is continuous and convex on f, then there exists definitely x bar minimizing f over f, and it is going to be a global minimum, right? And then this is not the most general result for existence of minimum and things like that. That's the nice thing about convex problems, is basically you have these global minimum and things like that, and they're quite have good structure and things like that. So there are very nice algorithms that can be used to solve any of the convex problems. That's why people talk a lot about convex optimization. But there is a slight generalization called quasi-convex, and then the definition is something like this. Instead of looking at the line, we just look at the maximum of these two. So slightly more. So if everything is convex, if a function is convex, certainly it's quasi-convex, right? Prove that as an exercise. And in fact, the result that we just stated for convex sets is also true for quasi-convex sets. If something is a local minimum, then basically it's global minimum. So technically this f in both these results should have been over some ball around the x bar. Okay, so why did we digress and then talk about convex sets? Well, I mean, many a time basically we solve optimization problems that are non-convex, but somewhere we try to hopefully find a convex region in that, and then try to find the answers and things like that. And in fact, as you will slowly see, that basically all the problems that we solve using the techniques that I'm going to present in a second belong to convex optimizations, and then convex optimization, and there are nice computational algorithms, right? So unconstrained convex optimization is one of the easiest optimization in a continuous space, right? The most difficult, I believe, is basically the discrete version with large number of, everything else is somewhere in between. So now let's actually get to some of the classical results that we are aware, and then you probably know every result that I'm saying, but I want to go through this carefully. So if you have unconstrained optimization problem, what we mean by that is f is nothing but an open interval, and of course the small f is basically a smooth function. We don't need smoothness in terms of all derivatives, but I'm going to assume that anyway. The problem is finding the solution over the interval, the minimum of this particular function f. So I'm going to put necessary and sufficient conditions and then go back and discuss what we mean by that at a high level. We're not going to get into too many mathematical details because they can be quite subtle. So anyway, the statement is something like this: if x bar in this AB solves the minimization problem, then the first derivative of x bar and is 0, and the second derivative of x bar is non-negative, right? And the sufficient condition is very similar, but some small subtle difference, which is quite an important difference. If you have some x bar in AB such that its first derivative is 0 and then the second derivative is positive, then x is going to be a local minimum. Now the difference, of course, as you can see, is in the second derivative, whether it's soft or strict, right? And that makes all the difference. Otherwise we would have had a set of two conditions that are necessary and sufficient. Unfortunately, this gap is what is going to pose a lot of issues for any of the optimization guys, right? So I mean, these results say if x bar satisfies something, then it is minimum, or if x bar is a minimum, then something is true. But it's possible very much that if you have a minimization problem, you may not have a solution, and we will see some of these examples. And but on the other hand, if it is a closed set, instead, if you take AB, then we assume smoothness anyway, then analysis guarantees that we have such a minimum. But unfortunately, it could be on the boundary, and when you're on the boundary and it's not easy to see without seeing the proof, these necessary and sufficient conditions may not be valid, right? So let's actually understand this one better by actually proving. So first things first, the problem basically minimum of this f of x may not have a solution. Okay, so suppose let's say this is a 0, 1 interval without including these two, and you can imagine sorry, let's make it simpler, not this, but in 0 infinity is our interval, and then imagine a hyperbola, something like this, right? On this 0 infinity, which is an open interval, right, without including both of them, do we have a minimum? Unfortunately, this this is probably asymptotically approaching some number, let's say 0. If this is 1 over x, let's say 1 over x is approaching 0 but never equal to 0, so this problem need not have minimum. And then I urge you to think of multiple examples where such thing can happen, right? So now let's actually go back and look at the necessary conditions and sufficient conditions. What we said is basically f of x bar is 0, f prime of x bar is 0, and then f double prime of x bar is non-negative, and this is a necessary condition, right? Okay, so what we have to do here is, we know that this x bar is a local minimum, so that means f of x bar is less than or equal to f of x for all x in some region, okay, around let's call B or something like that, which is a subset of AB. Okay, I didn't really define what is a minimum and things like that, but basically whenever we say something is a minimum, we actually do not mean minimum over the entire range that we are necessarily discussing, but it's probably locally minimum, right? If it is true at the entire space, then we call that as global minimum. We already used that terminology while discussing convex functions. Okay, so I'm going to be a little bit loose here, and then basically say we use Taylor series expansion, let's say something like this. Okay, plus I'm going to say x minus x bar square. Okay, and that's equivalent to basically saying f of x bar, x minus x bar is greater than or equal to 0, okay, for all x bar, this should be ball of x bar, sorry, for all x in the ball of x bar, so that means some small ball around x. Okay, now the thing is basically this x, if it is in the ball, basically either side of x bar, so this particular part could be negative or positive, whereas this is some constant because it's evaluated at a single point. So therefore the only way this can happen is f prime bar is 0, right? So hopefully you see that fairly obvious. F prime of x bar is 0. Okay, so I'm going to repeat that argument once again. Basically, this f prime times something is greater than or equal to 0, but that something so is arbitrary that we can actually change the sign at will. So basically if this is a positive quantity, this shows that f prime is non-negative. If this is a negative quantity, that shows that f prime is actually non-positive quantity. That can only happen if f prime is actually 0. So again, f of x bar is less than or equal to f of x bar plus f prime of x bar times x minus x bar, and then I'm going to basically go slightly higher and then go for this second derivative, half x minus x bar. This is the Taylor series expansion. I hope you're familiar. And then higher order terms, x cube, let me say. Okay. But we know that this is 0, right? And then this and this cancels. So this implies f double prime of x bar half times x minus x bar whole square, ignoring that higher order part, is greater than or equal to 0 for all x in the ball, I don't know, x bar, right? But this one is a non-negative quantity, so that implies this f double prime of x bar is greater than or equal to 0, right? So that's necessary condition, but when it comes to showing sufficiency, you pretty much reverse. We just have to be careful. Unless we have strict nature of this thing, we cannot, this whatever the error that we left over can actually ruin this sign and things like that. So that's why we need f double prime of x bar greater than 0, and then reverse the argument, and you can show that it to be a sufficient condition. So but the question then we have to ask ourselves is basically, can we not have the same condition? So for example, the necessary condition, can we guarantee, can we somehow conclude f prime could be strictly greater than 0? Well, f double prime, I mean. So unfortunately, let's say f of x is equal to x power 4 over the entire real line, and we know that the minimum exists at x0, something that for you to convince yourself, but f prime at 0 is 0. So you can have a minimization problem, perfectly valid, and not have the strict positivity of a second. I mean, 0 is a minimum there clearly, but in fact it's a global minimum, but yet f double prime cannot be positive in this particular case. Conversely, if you actually pick this function to be x cube, if somebody is interested, basically that looks something like this. It doesn't have a minimum or maximum in this entire interval, but if you actually look at 0 point, you will have f prime of 0 is 0, f double prime of 0 is also 0, right? So because of the fact that this is not positive, we cannot conclude, right? So but it's not, we cannot somehow expect that necessary condition can also be sufficient condition. So so that is in a way basic optimization problem. So let's pause for a second and then basically get to the second part of this particular lecture.